Okay, so we've got a very special integral today. Let's just hop straight into it. We've got the integral from negative infinity to infinity of 1 over x to the 8th power plus 1 dx. If we graph this, it's going to look something like this. It's symmetrical. It's an even function, like cosine x. The way we're going to be doing this is via complex analysis. I'm unsure whether this is factorable. It's factorable using complex numbers, but that's going to be incredibly hard to evaluate. So let's just hop straight in, complex analysis. We're going to define f of z to be 1 over z to the 8th power plus 1. Okay, and we want to find the singularities of this function, otherwise known as the values for which this goes up to infinity or negative infinity. Basically the values for which this is undefined. Okay, so we're going to let z to the 8th power plus 1 equal 0, because when this denominator is 0, this is going to be undefined. We get that z to the 8th power is equal to negative 1, which is also equal to e to the pi I, and e to the pi I is the same as e to the pi I times 1. Okay, that's uncontroversial, which is the same as e to the pi I times e to the 2 pi I k, which is just e to the pi I 2k plus 1. Okay, and for any value of k, this here is equal to negative 1, which is equal to z to the 8th power. But let's write 8 values of k, so let's say that k, the set of k values is 0, 1, 2, 3, and so on. And when plugging any of these k values in here, you get negative 1. So let's take the 8th root of both sides, so we get that z is equal to e to the pi I over 8 times, firstly 0, 1, 2, etc. So let's just write all of them here. E to the 3 pi I over 8, and so on. I'll write this quickly. And essentially for all of these values, when you take them to the 8th power, they just yield negative 1. And so when you put these into this function, it's undefined. And if you haven't done complex analysis before, it might seem that functions being undefined at a certain point is a bad thing. And it is, but just because they're undefined doesn't mean that they're not useful to study for certain integrals. Okay, here's our full set of z values. For any of these values, plugging them into this function will make the function undefined. Let's go ahead and plot these on an Argand diagram. We've got our real axis and our imaginary axis. So, one thing to notice is that they're going to be evenly spaced. So, the first one is going to be a quarter rotation about this first quadrant, let's say around here. Let's take this to be 1. Okay, so it's going to be around here. And the second one is going to be around here, sort of 3/4 rotation. Here's the 4th, 5th, and you can see the pattern they make. 5th, sorry, 6th, 7th, and finally the 8th singularity. And for any one of these values, when you plug it in, this function is not defined. Okay, so let's continue. We're going to define a contour. This isn't to scale, but we're going to have a contour with a semicircle, radius big R, cuts across the real axis. This is our contour C, and this section here we'll call this gamma. Why not? Let's call it gamma. Okay. We get the closed contour integral over C of f of z dz is equal to the integral from negative r to r of f of x dx, because we're working with the real numbers here, plus the integral over gamma of f of z dz. Now we can calculate all of these except for this one, because of course this is the original question. It would be circular logic even if we could calculate it without complex analysis. So let's start off by integrating this one. I should say also r is greater than 1, so that r encapsulates these 4 singularities here. We can calculate this one, this contour integral, by calculating the residues, summing them up and multiplying them by 2 pi I, which we will do. But first I want to find the value of this one here. Okay, so we're going to get the integral over gamma of f of z dz. Now you could parameterize this semicircle, substitute in e to the it into this, and there might be some way to do that. I don't want to, because I think it's not going to be easy. So what I'm going to do instead is use estimation to work out what this integral is. Okay? So we'll take the absolute value. The absolute value of the integral is less than or equal to the integral of the absolute value. Right? Let's write this in full. Because obviously if you're integrating and then taking the absolute value, you're absolute valuing, you know, positive and negative values added together potentially. Whereas if you're integrating this, you're only adding up a bunch of positive values. Okay, and then we're going to study this denominator a bit more. So z to the 8 plus 1 can be written as z to the 8 minus minus 1. Okay? Now, the reverse triangle inequality states that the absolute value of a minus b is greater than or equal to the absolute value of the absolute value of a minus the absolute value of b. Okay? So, we get that the absolute value of z to the 8 minus minus 1 is greater than or equal to the absolute value of z to the 8th power minus the absolute value of minus 1. Okay? This function here is equal to the absolute value of z to the 8th power minus 1, because the absolute value of negative 1 is just 1. And now let's go back to the diagram. as you see, this is a semicircle. So whatever point on this semicircle you have, the absolute value is just equal to the radius of this semicircle, which in this case happens to be big R. So let's substitute big R for the absolute value of C. Absolute value of R to the 8 minus 1, and as we stated earlier, R is greater than 1, so we can just get rid of these absolute value symbols since it's not going to be negative. Okay, so we get that the original statement that the absolute value of the integral over gamma of 1 over z to the 8th power plus 1 dz is less than or equal to the integral of this absolute value of f of z. Okay. So now we need to look if this is less than or equal to this. If we reciprocate both sides, we get that 1 over the absolute value of a minus b must be less than or equal to 1 over r to the 8 minus 1. Because obviously if you take the reciprocal, you reverse the inequality. Thus, this must be less than or equal to the integral of over gamma of 1 over r to the 8 minus 1 dz. This is just a constant. This is just z over r to the 8 minus 1 or something like that. And if we take the limit as r goes to infinity, this obviously becomes 0 because r grows away faster than z does. So this goes to 0. So we get that this original integral, the absolute value of that is less than or equal to 0 as r goes to infinity. The only way that this could be true is if this original integral here goes to 0. So now let's assume that r goes to infinity. That means that this right here goes to 0. If r goes to infinity, this is just negative infinity, positive infinity, which is our original integral. So we finally worked out that the original integral is just equal to the contour integral over this whole thing basically. And we can in fact evaluate this using Cauchy's residue theorem. Okay? Now Cauchy's residue theorem states that the value of a contour integral of f of z dz over the contour c is equal to the 2 pi I times the sum, the residues of the singularities encapsulated within this contour. And now there are 4 of them here, so we need to calculate the residues at each one of these points, and finally the value of that we multiply by 2 pi I to get a final answer to the original integral, because these two are equal. So to calculate the residue, we take, if we calculate the residue of a singularity of the function f of z, take the limit as z approaches, let's call the limit point a, of a minus z times f of z, this is equal to the residue of a. Okay, so let's go ahead, and our residues are these first four. So we need to calculate the residue of e to the pi I over 8, e to the 3 pi I over 8, e to the 5 pi I over 8, and e to the 7 pi I over 8. We need to calculate the residues for these values. Okay, so let's begin. So the limit as z goes to first one, e to the pi I over 8 of e to the pi I over 8, and our f of z is 1 over z to the 8th power plus 1. Let's just rewrite this as z to the 8th plus 1. We can see that this, by L'Hopital's rule, is just, minus z. Let's just rewrite this as z minus that. Yeah, z minus that. By L'Hopital's rule, this is just 1 over 8 z to the 7th power, which is just 1/8 times e to the negative 7 pi I over 8. This is our first residue. Let's just call this little r1. So r2, we're going to get the lim as z goes to e to the 3 pi I over 8 of e to the 3 pi I over 8 minus z minus over z to the 8th plus 1. By L'Hopital's rule, we get 1 over 8 z to the 7th, 1/8 e to the negative 21 pi I over 8 is R2, and instead of going through this whole process, let's just plug in the singularities into this function here to get immediately the limit value. There's nothing wrong with that, we're just cutting out a few extra steps. So we get that R3 is nothing other than 1/8 e to the negative, what's that, 35 pi I over 8, and R4 is 1/8 e to the negative 49 pi I over 8. Now if we sum up all of these values, multiply by 2 pi I, there is our final answer. So, the integral negative infinity to infinity of 1 over x to the 8th power plus 1 dx is equal to 2 pi I over 8. We're going to factor out this 1/8 power, then we get the sum of these added together. We can rewrite this R2 as e to the let's write the 1/8 e to the negative 5 5 pi I over 8, right, because factoring out a 2 from the top, it's just 2 plus 5 over 8, this fraction. Same deal here, this is just 1/8 e to the minus pi I over 8, and this one here is just e to the minus 3 pi I over 8. Okay? So we get e to the minus pi I over 8 plus e to the minus 3 pi I over 8 plus e to the minus 5 pi I over 8 plus e to the minus 7 pi I over 8 is equal to just pi I over 4 times e to the negative pi I over 8. That's just cosine of pi over 8 plus I sine pi over 8. I could show rigorously what all these are, but I feel like at this point we've evaluated this. Let's just plug it into a calculator, and you can verify this for yourself. Just one moment. And what's beautiful about complex analysis is it will just give you the straight answer. And there are surely ways to integrate this using real functions. Partial fraction decomposition might work. But when you understand how to do complex analysis, there's no harm in just taking the shortcut. Okay, so finally we've arrived at an answer. This right here is approximately negative 2.613, etc. I. These negative and i's cancel out, so the final answer is just pi over 4 times this, which is just approximately 2.0523 ... And I'm not sure whether there is an explicit way to represent this. It's going to be something in terms of pi, but the most important thing is we got this answer. It's around 2.05 for this integral. If you took your time, you probably could work out a value in terms of pi, but then you need to know sine of pi over 8, which is, it's not easy to evaluate. But anyway, I hope that this was helpful. We've arrived at a final answer, and I just want to verify that this answer is correct. So I'm just going to use Desmos to get this. Please bear with me. And yeah, Desmos is saying that this is correct. So I hope that this was helpful. I hope I was clear in all these steps. I used up all the way to the bottom of this canvas. Yeah, I hope that this was helpful, and I hope hope that I taught you a little bit about complex analysis.